Assalamualaikum. Hi everyone. I'm Cikgu NISWAN. In part 1 video, you have learned when principal quantum number of atom n equals to 3, number of subshells and type of orbitals also 3, meaning that the atom will have 3 types of orbitals, 3s, 3p and 3d. But looking at electron configuration notation of chlorine atom, perhaps you wondered what happened to the 3d orbitals of chlorine. Actually, electrons do not start occupying 3d orbitals until the 4s orbital is filled. Why is it so? In an atom, the orbitals are filled in order of increasing energy, starting from 1s, according to 3 rules. But before that, you must know an aid to remembering the order of filling of orbitals. You can start with an idea and write on paper like this. When n equals to 1, there is one type of orbital, it is 1s orbital. When n equals to 2, there are 2s and 2p orbitals. When n equals to 3, 3 types of orbitals, 3s, 3p, 3d. If the n is 4, there are 4 types of orbitals, 4s, 4p, 4d, 4f. That's the main idea you must have first. The orbitals in the increasing order of energy levels can be predicted from the illustration here. Starting from 1s, we will get to 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. So, based on that illustration, relative energy levels of the orbitals are like this. And in terms of energy levels, 1s is lower than 2s, lower than 2p, lower than 3s, lower than 3p, lower than 4s, lower than 3d, lower than 4p, and so on. Of Paul principle, Pauli's exclusion principle, and Hund's rule are used to determine the electronic configuration of atom of n elements. Here, we have chlorine atom with 17 electrons. Applying of Paul and Pauli exclusion principle, 1s orbital is filled first, since it is the lowest energy orbital. We must draw the 2 electrons in opposite spin, like this. You can see here, maximum 2 electrons can be filled in one orbital. Then, we fill the 2s orbital. Maximum 2 electrons with opposite spin. And now, 13 electrons left to be filled in the remaining orbitals. Now, we get to 2p orbitals, which consist of 3 degenerate orbitals. There are 2px, 2py, and 2pz. Hund's rule need to be applied here. Each orbital must be occupied singly, keeping electron spins the same before they are occupied in pairs. I use arrows pointing upwards first, then followed by arrow pointing downwards, like this. And then we continue to fill the next orbital. That's why The electronic configuration of chlorine atom is written as 1s2, 2s2, 2p6, 3s2, 3p5. Now, recheck your understanding. Students, notice that even chlorine atom has 3d orbital. It is not occupied. Electrons do not occupy 3d orbitals until the 4s orbital is filled. The 4s orbital will start to be filled for element in period 4, as you can see here. The 4s orbitals start to be filled. Prior to filling up of orbitals with electrons, the energy level of the 4s orbital is lower than 3d orbitals. But this is when the 3d orbitals are empty. See, energy level for 4s is lower than 3d. But on being filled, the 3d electrons repel the 4s electrons to a higher energy level. Means the energy level order are reversed. Now, the 4s energy level of being higher than the 3d. Example, for scandium atom here with 21 electrons. Electron will start to use a 3d orbital. Hence, when stating the electronic configuration of scandium atom, it is written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. Okay, the 3d orbitals are written first, followed by the 4s orbital. Students, you would expect the filling of electron pattern apply to all elements through vanadium with proton number 23. However, an unexpected deviation from the pattern occurs with chromium and copper. Why do chromium and copper have electronic configurations that are different from what you would predict? Why I say so? Look at this. We expect electronic configuration of chromium is 3d4 for s2. But experimental evidence, meaning that the observed configuration of chromium is 3d5 for s1. The experimental evidence indicates that some atoms achieve greater stability with electron configurations that do not conform to predicted patterns. For chromium, the greatest ground state stability results from a configuration in which its 4s and 3d orbitals are half-filled. 4s1 is said half-filled, 3d5 is said half-filled. For copper, a half-filled 4s orbitals, okay, half-filled 4s1, and a completely filled 3d orbitals, okay, 3d10, gives the most stable configuration. Similar situations arise for a number of atoms in the remaining periods. Students, before I proceed, I would like to introduce simplified notation of electronic configuration. This notation places the electronic configuration of the noble gas of the previous period in square brackets. Look at this example. We have sodium atom with electronic configuration of 1s2, 2s2, 2p6, 3s1. You see, the core electrons here refer to the electrons in the inner shells or inner orbitals. Okay, 1s2, 2s2, 2p6 electronic configuration will be equal to the electronic configuration of neon atom, which is located in period 2 compared to sodium atom, which is located in period 3. Thus, the abbreviation is written as neon square bracket 3s1. Second example, for calcium. Okay, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The core electrons, of calcium atom is the same electronic configuration of argon atom. That's why the abbreviation is written as argon square bracket 4s2. Please check with your teacher, is the abbreviated electron configuration can be used in an exam. Students, what about electronic configuration of ions? Electrons occupy the higher energy level are further away from the nucleus. The further away the electron is from the nucleus, the weaker the attraction force between the nucleus and the electrons. When electrons are lost in the formation of positive ions, the electron furthest away from the nucleus will be removed first. Thus, in this example, we have zinc atom with electronic configuration of argon 3d10 4s2. Zinc will lose its 2 electrons in its 4s orbital to form Zn2 plus ion with electronic configuration of argon 3d10. Copper atom with electronic configuration of argon 3d10 4s1 will lose its 1 electron from 4s orbital and form Cu plus ion with electronic configuration of argon 3d10. That's all for today, students. See you in the next section. Bye!